Last lecture we saw how to compute tree decomposition. Today we will how to compute tree decomposition approximately. Tree decomposition approximately. In today's lecture we will see some further applications of tree width. Okay? But before we do that, let us try to recall the argument for computing tree decomposition approximately, because we did it slightly fast in the lecture. So, what did we do? So, our algorithm had the following property. What is the property of our algorithm? So, our algorithm took as input a graph G, a number K, okay, and what does it output? It outputs two things: either tree width of G is more than K, or txt a tree decomposition of width 4k plus 4, or in other words outputs such that any bag has size 4k plus 5. Okay. Okay. So, this is what our algorithm did. Either it outputs G or. So, how did our algorithm? So, if you recall, we had this nice existential algorithm, which basically, because for the recursive nature of the algorithm, actually what our algorithm will do, our algorithm will take a graph G, a set W of size 3k plus 4, okay, and output a tree decomposition xt such that W is contained inside XR, the root bag. Okay. So, this is how we designed our algorithm. Okay. Okay. So, let us just try to so, okay, this is what we will try to do. So, what are the steps of our algorithm? So, the algorithm is a recursive algorithm. It's a recursive algorithm. Okay, it's a recursive algorithm, and it works as follows. It just check. So, first of all, you know that if the graph has tree width k, then the number of edges in this graph is upper bounded by n times k. So, you could have a basic test if number of edges in the graph is more than nk, return tree width of G is more than k. Okay. So, these are like some of the basic tests that we could perform at any point of time or just before even algorithm starts. Okay. And now, what does algorithm does? So, algorithm will take a particular graph G, it takes a set W and it will construct the required. So, first thing we check, what is the number of vertices in my graph? If the number of vertices in my graph is upper bounded by, okay, if the number of vertices in this graph is upper bounded by 4k plus 5, then we output our tree decomposition of one node. Okay. What is that? So, this is it, and the XR, because R is basically vertex set of G, and it automatically satisfies all the property. Otherwise, now we are in the case when vertex set of G is strictly more than 4k plus 5, and we are given a set W. So, if you recall correctly, how did our algorithm proceed at this point of time? We said, okay, let us fix a function f from Vg to 0, 1, okay. And what is the property of this function is that f of v is equal to 1 if v belongs to capital W, equal to 0 otherwise. And we know that if tree width of G is at most k, then there exists a set S of size k plus 1 such that what happens is that here is set S, and look at any connected component, okay, any connected component C1 to Cm, Ci intersection W is upper bounded by W by 2. So, if a graph G did have a tree width at most k, then there is a property that you can find a set S of size at most k plus 1 such that if I delete this, then every connected component of G minus S contains at most half the vertices of W. Now, we did not know how to prove this algorithmically, but we observed something interesting. So, what was that? This is the place where say let us try to reduce the problem to ST separator. Okay. So, rather than what are we looking? We say, look, it is difficult to find S maybe, but can we find, say, let us call it S star such that if you look at components now C1 to Cm, what is the property that Ci intersection W is say at most 2/3 of W. So, I am saying that look, I cannot guarantee that I can find such a S efficiently. Of course, we could have found like in n to the power big O of k time we can find, you try all possible k size subset, k plus 1 size subset, and you have found it, but we do not want to do this. So, what we said, okay, fine. So, what could be? So basically the idea is that look, here is your S and here is your, so let us, okay. So, S here, these are the vertices of W. Now, our idea is that is it possible that look, the W is small. So, we can guess which vertices, okay, right. W is just W had size 3k plus 4, right. So, what we could do? So, guess W intersection S, not a problem, right. We can guess because it is only 3k plus 4. Now, if we could partition W minus S, let us call this Y, W minus S into A and B such that mod A is at most say 2/3 of W, mod B is at most 2/3 of W, and then find a separator of minimum size, okay, find a separator of minimum size, okay, such that this and this, then find a separator of minimum size, okay, then find a separator of minimum size, then it will guarantee that every component, say minimum size, say V, that every component of G minus Z union Y has either A vertices or B vertices, okay. And what is the property? So that implies that C, like any component here, C intersection W is upper bounded by either A, or C intersection W is upper bounded by B, which is 2/3 of W, and it is at most 2/3 of W. Okay. But the question arises, okay, that's fine, but why does a minimum separator of size k plus 1 minus y exist? Not clear, right? Yes, this is true that a minimum separator will have the property, okay, minimum separator will have a property that if I find an A and B, grouping of W minus S into A and B such that A is at most 2/3 of W, B is at most 2/3 of W, and then we find a minimum separator, say Z, then of course if I delete Z union Y, then I know that no connected component will contain both vertices from A and B, because we have find a separator, we have been able to separate this, and this is very easy to make such a ST separator problem, because this is like your A, this is like your B, this is like A, B, you just make S, make adjacent to S, and then like, yeah, then you can make a ST separator. But more importantly, why does a minimum separator of size k plus 1 minus y exist? So to do that, what we actually can show is that look at this S and look at this, like we will be able to group some of these patches into A and some of these patches into B. So now if I can group some of these patches into A and some of these intersection into of B, some of these intersection into B, then what we know? Then definitely the S, which was a half W by 2 separator, is also a separator of the kind which will separate A from B, and that immediately implies that there is the min separator has to have a size k plus 1 minus y. And last time we saw that look at these patches, what we called it. So we called it W, we call these patches as, let's call it XR, XY is overly used. So let's call it, let's call these patches, this is also overly used notation, let's call it I, okay. Okay, let's call it DI is CI intersection W, okay. And if you recall correctly, we call this, and suppose we had the size D1 dot D1 DM CI intersection, okay, and suppose DI has side N1 and DM has side NM, and then we were able to show that, okay, well, then we can find a partition into A and B such that mod A is at most 2/3 of W and B is at most 2/3 of W. Okay. So we knew how to do this, we saw in this slide. So this is exactly what we do. So look, I cannot, so which implies that we have such a good S, right? If we have such a good S, then actually there exists a S star with the property that each of this component has at most 2/3, and in fact this can be done by partition of WS into A and B of size at most 2/3 of W and finding a min separator. So our algorithm is very simple. So what our algorithm does at any point of time, it takes W, partitions into 3 parts, A, Y and B. And how many such partitions are there? 3 to the power 3k plus 4. And in G minus Y, what does it does? In G minus Y, finds a min separator between A and B. And what did we call that? We call that Z, okay? Okay, Z, okay. Now, if cardinality of Z is greater than k plus 1 minus y, invalid partition, okay, and if all partitions fail, what do we know about it? If all partitions fail, what do we know? Like, we know that if the tree width has at most k, then there exists a good partition. So, if all partitions fail, we can immediately conclude that tree width of G is more than k. Else, some partition succeeded. Else, some partition succeeded. And even if one partition succeeded, you can make a progress. So, how will we do this? Then you will look at Y union Z, okay, and okay, this is your potential, this is your S star, and you look at your components C1, C2, Cm, and what are you guaranteed that Z intersection this Ci is at most 2/3 of W. So, what you do? You recursively solve problem on Gi, which is graph induced on Ci union S star, and you assign Wi. So, what is Wi? Wi is W intersection Ci union S star, right? Now, what is the size of Wi? Well, of course, the size of Wi is plus C star. This is at most 2/3 of W. Size of S star is at most k plus 1, right? Well, so what is this? 2/3 of W, which is like 3k plus 4 plus k plus 1, which is 3k plus okay. So, what is this going to be? This is going to be 8/3, okay, plus right, plus 1. Now, 8/3 plus 1 I claim is strictly less than 4, right, and this is easy to take because it is 8/3 is less than 9. So, this is strictly less than 4, which implies this is strictly less than 3k plus 4. Now, okay. So, this definitely implies that Wi satisfy this inductive recursive definition of the algorithm, that the cardinality of Wi has to be at most 4k plus 4. Okay. One thing which I missed out when trying to explain to you is that okay, this W at any stage, if W size is less than 3k plus 4, we arbitrarily add vertices from outside to make it size 3k plus 4 exactly. Okay. Now, what does this implies? This implies two things, that look, then it's some vertex of W, some vertex, this also implies that some vertex of W, some vertex of W does not appear in GI, which implies the cardinality of VGI is strictly less than Vg, and hence we make some sort of progress. So, you recursively solve the problem on this smaller instance. And you recall correctly, once we got the small tree decomposition for all these components, we designed a tree decomposition of the whole graph by adding a root and making it adjacent to root of each of these guys, and what did we assign to x of r? So, we assigned x of r is nothing but W union S star, and this is why the tree decomposition of this algorithm is upper bounded by cardinality W, cardinality S star, upper bounded by this, which is 3k plus 4 plus k plus 1, which is 3k plus 4k plus 5. Okay, 4k plus 5, and hence we have been able to output decomposition of width at most 4k plus 4. And then of course, you could ask, what about running time? So, well, the running time of this algorithm is essentially, if you notice, is like T of n is like upper bounded by summation some T of ni plus like where there will be plus some 3 to the power, I would say 3k plus 4 times some k to the power big O of 1 times n, and this is like you have to be a bit careful because these are like what is this a property? So, the property is that if you sum ni minus k, then it is equal to n minus k plus 1, actually n minus, right, because in each of this component there is a k plus 1 size which is common. So, you have to take max over all possible partition of this, and by a simple induction you can show that this is actually an algorithm with running time 3 to the power 3k times n square. Okay. So, this will come to you 27k big O of 27k times n square. So, but I will leave this is via induction. Okay. So, I hope this algorithm is little bit more clear to you now that we have redid it. Okay. So, basically this is an algorithm which we looked at this existential algorithm or the existential proof that gave us this upper bounded by 3k, but notice that when we went to the constructive we lost another factor by k plus 1, because existential we could guarantee that the W gets split very balanced at most half, but algorithmically we could only get 2/3, and there is no magic about 2/3. If you could only guarantee say even just slightly less than 1, say maybe say 4/5, then the factor of approximation will change, but you still be able to get some C power k approximation algorithm. So, you will make progress even if the W is at most a constant fraction of what we started with in each of these things, but then you have to make the whatever the initial bag that you started with big enough so that this math holds. Okay. So, I hope all this is good. Okay. And so, now what I want to tell is some applications. So, now we will move to applications. Okay. So, some applications we have already seen. Dynamic programming algorithms over graphs of bounded tree width, right. So, we saw that we saw an algorithm for max bit independent set, 3 coloring. Then we also saw an algorithm for dominating set. We saw an algorithm for Hamiltonian cycle, right? And we showed that all these problems are FPT parameterized by tree width. Okay. So, yes, so tree width is an interesting object, but one natural question arises, like the art of doing DP looked very similar. So, a natural question was, can this process be automated? Can this process be automated? Could we prove some general meta theorem, right? And what I mean by could we prove some general meta theorem? So, in these things what happens is that you say, look, generally these meta theorems are like, so if this part of the, like this next 10 minutes of lecture, even if you do not follow completely, it's perfectly fine. So, we say, could we find a fragment of logic, okay, such that we can say if a problem is expressible in this logic, then our DP algorithm can be automated, okay. Or rather, if a problem is expressible in this logic, then I would like to say, then the problem is FPT parameterized by what? By size of the expression plus the tree width of the graph, okay. And this was proved by Kurzweil, and this is also called CMSO2, like or extended monadic secondary logic. So, this is a logical language and graph, and which has following properties, okay. So, it has some logical connectivity like and, or, implication, not, equal. There are quantifiers over, like for all that exist over vertex and edge variables. There is a predicate to check whether two u and v are adjacent. There is a predicate to check whether some vertex is incident to some edge or not, and there is also a quantifiers for all that exist over vertex or edge set variables. I think this is just repeated. So, this is okay, and we can also check something is an element or subset of some vertex edge subset. So, for example, look at the formula. There exists C subset of V for all V in C. There exists U1 comma U2 in C such that U1 is not equal to U2. Adjacent of U1 V and adjacent of V2 is true. What is the meaning of, like, what does this formula, if a graph satisfies this formula, what does this mean? It will mean that if a graph GV is true only if graph has a cycle. Why? Because what are we saying? C, there exists C subset, like who will satisfy this formula, right? So, only those graphs will satisfy this formula if it has a cycle. So, what are we saying? Look, C is a subset of V. For all V in cycle, for all, there exists two other vertices in C which are not equal to and U and V are V is adjacent to U1, and so basically I looked at V, I say, look, for every vertex I can find two other vertices to which it is neighbor to. So, that will only happen if a graph G has a cycle. So, for example, this.